Hi, my name's Will Krosick, Scientific Services Manager at Chemical Computing Group. Today I'd like to show you how to align the sequences of two or more proteins and superpose their structures. Specifically, we'll look at how to handle multimeric proteins and how to use Dendrograms and other visualization tools to help with the interactive analysis. So let's get started. So I'm just going to go ahead and open the structures that we're going to be working on today. I'll grab these from our sample mol directory, and because I'm going to select more than one, I'll just hold down Control on the keyboard, select the ones I want, hit OK, and I see them appear here in the main mo window. Currently there's lots of chains that are quite disorganized. In order to organize them, I'm going to refer to the sequence editor, which, as the name suggests, we use to display sequences. This is also our launching point to the various protein modeling tools that we have in Mo. So I'm just going to make a few changes to how we display our sequence. I can see here we've got our 3 PDB tags, we've got 18 chains, but I noticed that some of these contain things that are not proteins. So for that reason, I'm just going to click the minus button to remove anything that's not a protein. And notice as well I have to scroll along to view the sequence. So what I'm going to do is just wrap the sequence and also switch to the single letter amino acid code. And I can also scale the font here should I wish. Because I know that we've loaded some antibodies into our system, I'd like to annotate these both in sequence and atoms simultaneously. So I can do that from the sequence editor by clicking Annotate and then Antibody, and I can choose between some of the common numbering schemes that we have available. Today I'm going to use IMGT, which splits our sequence into different panels. By default, our light chain is displayed in the leftmost panel. That would be subunit 1. In subunit 2 sits the heavy chain, and everything else falls into subunit 3. Notice that the sequence has been colored to show us the CDRs. So for the light chain, these are shown in purple, L1, L2, and L3. And for the heavy chain, we see H1 and H2 shown in orange. And the third CDR of the heavy chain is colored red. And that reminds us that H3 is more variable than any of the other CDRs. If I take a look in the main Mo window, I see that this coloring scheme has been extended to the main Mo window. So the atom sets are colored accordingly. And I pick out a purple CDR corresponding to a light chain here. But I noticed that this rendering scheme has been applied only to the antibody, not the antigen. I can control the antigen though using the sequence editor, so if I just right click on a selected chain and I can color my antigen in gold. So with that, I'd also like to visualize and start to think about the sequence similarity. So here I can plot directly in the sequence editor some different properties. I'm going to start with the sequence similarity, whereby these tall blue bars show me the residues that are similar. The tall red bars show me the residues that are dissimilar. Currently the sequences are not aligned, so the sequence similarity overall is quite low, and perhaps this is a good prompt to go ahead and align those. So for that, I'm going to open the Align Superpose panel, which is displayed at the footer of the sequence editor. It comprises 3 main sections. The first Setup Chains button allows control over setting up blocks for group-to-group alignments and subunit assignments when we're handling multimers. The middle part of this panel is for aligning sequences, and the third is for structural superposition. So you'll notice when the Align Superpose panel is open, we get this extra column displayed with the green asterisk showing us which alignment groups are going to be included in the align operation. I can change the alignment groups by using the Setup Chains button, which allows us to get control of aligning sequences when we want to keep a set of aligned sequences and align them as a group when we perform a group-to-group alignment. So here the top part of the Setup Chains button allows me to control this group-to-group alignment, but the bottom part allows me to manually set these up, which would be a good option if we're handling multimers. In this case, the step was automatically done for us when we did the annotation of our antibodies. As I mentioned, the green asterisk represents the groups that are going to be treated as individual sequences and not grouped together with any other chains. Chains marked with a red I are going to be ignored in the alignment operation, and chains marked with either A, B, C, D, or E are going to be grouped with other chains with the same letter and treated as a block in the alignment operation. Beyond setting up chains, we do have other options available to us. So for example, when it comes to alignment, we can align by sequence only, whereby, as the name suggests, we're not leveraging the structure, we align based only on the sequence. By default though, sequence and structural is selected by default, as I say. It's a good option when we have structural information available, when typically used when sequence similarity is low and we want to augment the signal using structure. Today though, we're going to use sequence only, and I'm going to start by aligning those structures. So notice here that the sequence moved, but the atoms in the main mode window did not. We see as well that blue bars now occupy most of our sequence, with the exception of the CDRs, which we typically expect, since we expect these to be different. In contrast though, the antigen is mostly red, and based on this alignment and this type of analysis, we can see that they're dissimilar, and there's going to be little sense in trying to superpose these. If we did, that would reduce the quality of our superposition, so we need to tell Mo to ignore these. I'm going to do that by selecting the antigen chain, and then I'll go to our Setup Chains button and hit I for ignore. So antibody chains that are marked with the green asterisks are going to be included in the superpose operation. Antigen chains that are marked with the red I are going to be ignored in the superposition, although they will move along with the rest of the protein chains. So I'll go ahead and click Superpose. This time the sequence does not change, but the atoms in the main Mo window do. And here we find that Mo has generated the best overall superposition of the three antibodies based on the current alignment of the sequences. This is exactly what we wanted Mo to do, and in doing so it's put equal weight on superposing all parts of the antibody structures. That being said, that we know the framework region as a fold which is much more conserved than the CDR loops, so perhaps it makes more sense to focus on the superposition of the framework region. If I want to quantify it, I get a readout here. I've got our RMSD of 3.402 across the entire structure. As I say, to get control over the framework region and performing a superposition on this region alone, if I just go to the main Mo window, open the system manager and pin that to the main Mo window as a means to manage all of the data that we have in our system, I notice that we have an entry here containing 17 sets. These were generated when we annotated our structures, and we find here collections of atoms that are grouped together as a set. And within here we've got our framework region, which I can select in the main Mo window, if I just go back to our sequence editor, I see that those same sets are contained within here. So that allows me to select the framework region, and I can perform a superposition on that region alone. So here I see the RMSD is much better, 1.237 angstroms, albeit just across the 179 residues that comprise the framework. Now, whilst talking about superpose options, I'd just like to introduce some additional options. The first would be refine with Gaussian distance weights, which will bias the superposition towards residues which superpose well. The second is to accent secondary structure matches, which will bias the superposition towards alpha helices and beta strands so that we can optimize the superposition of these secondary structures. So if we just recap, our structures are now superposed in the main Mo window. The atoms in a given tag were moved along as a group, so the antigen chains were moved too, even though they were set to ignored. We get quite a good superposition on the framework region if I just select that there, but we do see some dissimilarity in the CDR regions. For example, here the CDRs of the light chain, shown in purple. And of course the antigens are quite different. But we can further analyse our structures, and we have tools in Mo to facilitate this. As an example, we can use Dendrograms to explore the similarity of the tags or structures. So I'm just going to toggle that on, and by default we're going to be looking at the similarity. If I just hover my mouse over the branch of a dendrogram, I get a readout on the footer here, which is showing me that the bottom two structures are most similar. Remembering that our objective is to compare the sequence similarity of the three antibodies, what I'll do is just toggle on the option for the selected chains and go ahead and select the two chains for the antibody. So that would be the light and the heavy. And I can see here that the readout now on the footer of the sequence editor shows me that they have 73.2% similarity calculated over the entire light and heavy chain. Using the options, I could also look at RMSD should I wish, and I could look at RMSD across selected residues, which would give me the chance to be able to select the framework region and analyze the RMSD across that specific region, whereby again I find it's the top two structures which are most similar, with an RMSD of 1.08 angstroms versus 1.29 angstroms. Beyond using the dendrogram, we do have other analytical tools available to us. As an example, we can plot the RMSD, which opens a panel providing visual information in the form of a heat map about the superposition of our protein chains. The RMSD value of each chain pair is represented at the intersection of the column and the row by one coloured box. There's a coloured legend on the side here which is capped at 4 angstroms. I just want to give mention to one specific option that we have here, gapless columns, which when it's on it calculates the pairwise RMSD only with the columns in the alignment that contain no gaps. So we have corresponding residues for every chain. Otherwise, if I toggle it off, all possible residue pairs of the two chains are used when we calculate the RMSD values for each heat map cell. So in the final part of today's session, what I'd like to do is show you how to add a fourth structure to our analysis. Our objective will be to align and superpose the fourth structure to the existing aligned and superposed structures that we have in the main Mo window. So I'll just go ahead and retrieve our fourth structure. Perhaps I'll just type in 4 to get us there. This structure here, which I happen to know includes more than one antibody. So for that reason, I'll click on the symmetry pull down, select biomolecule assembly and hit OK so that I load in just one antibody. So again, this is disorganized and I'm going to organize it by firstly setting up our sequence editor. I see we contain some ligands here, so I'll click the minus button to remove anything that's not a protein. And next I'll want to annotate that fourth structure that's not yet been annotated. So again, I'm going to use the IMGT numbering scheme. And if I just click into space there, I can have a look at the RMSD for that fourth structure, which is quite large compared to the others. And of course we expect to see that because we didn't align or superpose this fourth structure yet. In doing so, I will have two options. Option 1 would be to simply repeat the steps that I took previously. So just realign, resuperpose exactly as I did before. Option 2 though would be to use blocks. And that's exactly what I'm going to do in the next steps. I'm going to want to treat the first 3 antibody-antigen sequences, complexes as a block, because we already went to the effort of aligning and superposing these. And then I'm going to align and superpose the fourth structure to that block. So what I'll do is go ahead and select the first 3, and I'll use the Setup Chains button to add a partition here, which will assign these first 3 structures to block A, and the fourth structure appears in block B. So I'm going to firstly align, which changes the sequence, but not the atoms in the main Mo window, and then I'm going to superpose, which is going to change the atoms in the main Mo window and superpose those. Of course, what I could do is, in this case, we had superposed using the framework region. And here I find that the RMSD is quite reasonable. I can look at this in detail here, so 3.04 Armstrongs, which is quite good. Let's look at the RMSD across the framework region. So if I just go back to the main Mo window, select the framework region, and I can see that we've got an RMSD of 1.08 there across those bottom two structures, 1.3 overall. So these RMSD values look quite reasonable, especially across the structurally conserved framework region of these four structures. Here we were able to add and analyze this fourth structure while keeping the alignment of the first three sequences as is. And that brings us to the end of today's session, where we learned how to handle multiple chains for protein alignment and superposition. We also learned how to annotate, align, and superpose using the sequence editor. And finally, we explored Dendrograms and other visualization tools to help with interactive analysis. I hope you've learned a lot today. If you have any questions, please do reach out to us at support@chemcomp.com.